Hello YouTube fam. Welcome back to our channel. In this channel, we will be discussing various topics in the exciting world of AI, machine learning, and computer vision. Our content is crafted by our awesome human team, but here's the magic. It's finely tuned and optimized by our AI wizards, bringing you top-notch information. And guess what? The presentation is delivered to you by our AI hosts and voiced by our incredible AI avatars. Let's get started. In today's video, we will discuss fine-tuning the vision language model called Llava. First, let us see what are vision language models. Vision language models are AI systems designed to understand and generate language based on visual inputs. They integrate visual data, such as images or videos, with textual data to perform tasks like image captioning, visual question answering, and image text retrieval. These models leverage techniques from both computer vision and natural language processing, often using large neural networks to learn from vast amounts of paired visual and textual data. By combining visual and linguistic information, they can generate more contextually relevant and accurate descriptions and answers. The main components of vision language model are image encoder. This part of the model looks at pictures and translates them into a form the computer can understand. Embedding projector. This part helps align or match the image data with text data. It's like a translator that makes sure both the image and text speak the same language to the computer. Text decoder. This part takes the combined image and text data and generates a response or description. Next up, we will discuss how to train the model. Unifying representations. The trick is to combine the image and text data in a way the model can use. Different approaches. Different models use slightly different methods to do this. The Llava model, short for Large Language and Vision Assistant, is a type of AI model designed to understand and generate responses that incorporate both visual and textual information. Here's a simplified breakdown of what it is and how it works. Llava is a vision language model that combines the strengths of image processing and natural language processing. It is specifically trained to handle tasks where both image and text inputs are involved, such as answering questions about an image, generating captions, or providing detailed descriptions of visual content. Let us look at different components. Clip image encoder. This part of the model is responsible for analyzing images. CLIP, Contrastive Language Image Pre-training, is a model developed by OpenAI that can understand images and text together. The image encoder processes the image and converts it into a format that the model can understand. Multimodal projector. This component helps align the image data with the text data. It acts as a bridge between the visual information from the image encoder and the textual information from the text decoder. Vicuna text decoder. This is the part of the model that generates text based on the combined image and text data. Vicuna is a language model that can produce coherent and contextually relevant text. Let us look at the training process. Dataset. The model is trained on a dataset of images and their corresponding captions. Additionally, questions related to these images and captions are generated using another AI model, GPT-4. Initial training. During the first phase, the image encoder and text decoder are kept fixed, not updated, and only the multimodal projector is trained. The model learns to match the image features with the text features by comparing its generated outputs with the ground truth captions. Fine-tuning. In the second phase, the image encoder remains fixed, but the text decoder is allowed to learn along with the multimodal projector. This helps the model generate better textual responses based on the visual input. Finally, let us discuss the applications of Llava. Llava can be used in various applications, such as image captioning, generating descriptive captions for images, visual question answering, answering questions based on the content of an image, multimodal search, searching for images based on textual descriptions or vice versa. Assistive technology, helping visually impaired individuals by describing images or scenes. In summary, the Llava model is a sophisticated AI system that excels in tasks requiring a deep understanding of both visual and textual information, making it highly useful in many practical applications. This work incorporates insights and code snippets courtesy of Hugging Face, published on Hugging Face's blog. We extend our gratitude to the original authors and Hugging Face for sharing their valuable resources with the community. Here are a few resources used for reference. hupmean/huggingface.cog/blog VLMS. Also, thanks Twitter user Menu Romero for sharing a sample notebook. x.com 8488/status 77888237085018007. We will run this on a Google Colab A100 GPU, A100-SXM4-40 GB. Before we look at the code, we will discuss one more concept. We will understand what is PEFT, Parameter Efficient Fine-Tuning. Parameter Efficient Fine-Tuning, PEFT, refers to a set of techniques in machine learning aimed at updating large pre-trained models in a way that requires altering only a small fraction of the model's parameters. This approach is particularly useful when working with very large models, where full model retraining can be prohibitively expensive in terms of computational resources and time. In the context of parameter-efficient fine-tuning for machine learning models, LORA and QLORA refer to specific techniques designed to update large pre-trained models more efficiently. LORA, or low-rank adaptation, is a technique used to fine-tune large pre-trained models in a parameter-efficient manner. Instead of updating all the parameters of a model, LORA focuses on adapting only a small set of parameters, typically by introducing and training low-rank matrices that modify the weights of specific layers, like the attention or feed-forward layers in a transformer model. This approach allows for significant customization of the model to new tasks with minimal changes to the overall parameter set, preserving the original strengths of the pre-trained model while adapting it to specific needs. Imagine you have a huge, complex book representing a large pre-trained model that you want to customize slightly without rewriting the whole thing. LORA allows you to do just that by adding a few notes or annotations, small changes, to some pages, making the book more relevant to your specific needs without altering its original content significantly. In technical terms, LORA introduces small, trainable adjustments to certain parts of the model while keeping the vast majority of the original parameters fixed. This makes the fine-tuning process much more efficient, as you're only tweaking a tiny fraction of the model. Let us see what is QLORA, or Quantized Low-Rank Adaptation. Quantization, in the context of machine learning, involves reducing the precision of the numerical representations used in a model. For example, reducing floating point numbers from 32-bit to 8-bit integers. This process helps decrease the model's memory footprint and can speed up inference, making the model more efficient, especially on hardware with limited computational resources or specific accelerators designed to work with lower precision arithmetic. Building on the previous analogy, if LORA is like adding handwritten notes to the book, QLORA is akin to using a shorthand or a more condensed notation for those notes. QLORA further compresses the changes you make, the annotations or notes, by quantizing them, which means representing these adjustments with fewer bits. This not only makes the fine-tuning process more efficient, but also reduces the memory and computational resources needed to apply these customizations. In very simple terms, both LORA and QLORA are about making smart, minimal updates to a large pre-existing knowledge base, the pre-trained model, to adapt it for specific tasks. LORA does this by adding small modifications, and QLORA goes a step further by compressing these modifications to be even more resource efficient. First, we will install packages. We will install transformers, PEFT, bits and bytes, orth, RL. Next up, we will load the model and quantization config. Next, we will define chat template and tokenizer and processor. Before fine-tuning, we will run inference for few samples. We ask the model to explain the image. It responds with, "The image features a toy camel with a pair of glasses on its face. The camel is wearing a pair of red glasses, giving it a unique and quirky appearance. The toy is sitting on a table, and its glasses are lit up, adding to its playful and whimsical charm." All right, now, let us prepare the data for fine-tuning. Create a data collator to combine text and image pairs. We will load the dataset. For faster training, create a new dataset with the first 5,000 elements. Now, we will see the most important customization. We will add the text AI bot hello to all the assistant responses after fine-tuning. We will check if the model has learned this pattern. Let us look at few sample data. We can see the questions and corresponding answers. For the question, who wrote this book? The answer is AI bot. Hello, Donna Eden AI bot hello. For the question, what is the title of this book? The answer is AI bot hello. The energies of love, using energy medicine to keep your relationship thriving. AI bot hello. After fine-tuning, we will check if the model has learned this pattern. We will then set the arguments for training. Do LORA configuration. Next up, we will create the SFT trainer object. Finally, we will run the fine-tuning training. We can see the loss decreases after each step. We started with loss of about 3 and have come down to about 0.7. Alright, we are done with fine-tuning. We will run inference on the fine-tuned model. For the question, who wrote the book? The model responds with AI bot. Hello. For the question, who wrote this book in the attached image? The model responds with AI bot. Hello. Similarly, for other questions as well, we can see the model respond with text containing AI bot. Hello. This shows that the model has learned the custom modified caption messages we provided during fine-tuning. We have successfully fine-tuned the Llava model for our own use case. Thanks for watching. Stay tuned for more exciting adventures in the world of AI and machine learning and algorithms. If you found this video helpful, don't forget to hit that like button. Subscribe for more tech talks and ring that notification bell to stay updated on our future explorations. Until next time, happy coding and keep the curiosity alive. Thanks for watching.